Thank you very much, and good morning, everyone. So, what did we do yesterday? So we constructed this cat-zero cube complex, this blow-up complex, on which the blow-up complex CS, where S was a regular projective surface. And we had like the vertices were of the form T phi, where T was a regular projective surface, and phi was a marking from T to S, and then we looked at the equivalence class like up to isomorphism. So these were our vertices. And then we saw kind of like we defined edges, which were given by blowing up points, and cubes, which were given by, well, whenever we see a cube in the graph, we add a cube inside here. And we saw this was cat-zero. Now, what is nice is that we have actually a group action by isometries of BRS on this cube complex. And well, the action is pretty straightforward. So if you have a F in here, then and we have a vertex of this form, then we just define F of T phi to be T F phi. So essentially, we just operate on the markings. So we change the markings. And now it's actually immediate from the definition that this is an isometry, right? Like we see that cubes are preserved, like edges are preserved, cubes are preserved. Follows directly from the definition. And well, yeah. So let's write this down. So it preserves the cubes. So it's an isometry. And also, what we also have is that actually it preserves the picker rank and it preserves the orientation of the edges. Like, right, we had like orientation on every edge, and this is preserved by this action. Good. And then, okay, so what we would like to do today is kind of like to better understand this action and to also to better understand the geometry of the cube complex and what does this action do. Maybe like the very first observation is, okay, if we have an action on a space, what we are interested in is, do we understand the stabilizers of points? So often when you look at an action of a group on some space, okay, it's always you need to understand the stabilizers of points. Kind of like, okay, worst case, you have an action group on a space where every element fixes a point. So, so in that case, for example, okay, it might not help us so much. But in this case here, let us observe if we have a birational map of S and we have a vertex T phi, which is stabilized by F. So this means this is the same as a T phi again, and this, I mean, we know, but it's just a T F phi. So now we just have to look at the definition, like when are these two vertices equivalent? This is the same as saying that phi inverse F phi, so that's a map, birational map from T to T. This has to be isomorphism, so it's an automorphism. So this means the vertex stabilizers, so they correspond exactly to the automorphism groups of these regular projective surfaces. And the phi kind of tells us how this is conjugated to this automorphism. And of course, that's good news, because we have a whole mini course at this summer school where we learn about the structure of these automorphism groups as well. So I don't want to say that's like easy, but it's still something which we understand fairly well. So in the rest of today, it's kind of like we want to rather look what happens, with elements in BRS that do not fix a vertex. So yeah, in order to understand this, we have to go back and do a bit more geometry, learn a bit more about the geometry on cat-zero cube complexes. So the important tool here are the so-called hyperplanes. So let me explain what this is. So if L is a cat-zero cube complex, and now if we have, okay, let's call it sigma, maybe, okay. Usually use this for a standard quadratic involution, but let's say this is a cube, an n-dimensional cube. So now what we want to define is what is this mid-cube. So if you have a cube, we can just look at kind of like mid-cube here, so like kind of in between. Yeah, we just look at this slice in the middle. That's called a mid-cube. Of sigma is, and I mean this one is now a square, so it's like this mid-cube is always like a n-1 dimensional cube. That's an n-1 dimensional unit cube. Containing the barycenter of our cube, so the middle point. And we want that it is parallel to one of the faces. Okay, and now we would kind of like to make this, to kind of like enlarge this also to other cubes. So basically what we do, we look at some equivalence relation on the edges of our cube complex. And it's just given by being parallel. So I consider the equivalence relation on edges given by, generated by, we say an edge E is equivalent to the edge F if E and F are parallel in some cube. So right here we can just continue like that. So, okay, these are all equivalent to each other. The back as well. So all parallel, and then we continue like that. And okay, if we have an equivalence class of such edges, this defines as a collection of such mid-cubes. That intersect the members of this class. And such a collection is called a hyperplane. A hyperplane in our cube complex L. And we will often denote this by, well, this equivalence class. Okay, so it's essentially we look at kind of like equivalence class of all parallel edges, and this defines as a hyperplane, so we can cut our cube complex. And here now I will use some fact from the theory of cat-zero cube complexes, which we will not prove. So, so one important fact is that the complement of such a hyperplane consists of exactly two connected components. The hyperplane E has exactly two connected components. Let's call them, and in addition, they are complex. Convex, not complex. Yes, so they are convex. The two connected components, and we will call them the two half spaces. Given by this hyperplane. And often we will denote them by E plus and E minus. Convex. This means if we have 2 points in there and a geodesic between these 2 points, it has to be contained in this half space. So we take 2 points in the same half space. You take a geodesic between these 2 points, then it stays within this half space. Either Euclidean or combinatorial. Yeah. Yes. So the hyperplanes, this works in any dimension. We just need a parallel, like this parallelism class. But of course, the hyperplane is also, again, infinite dimensional. Yeah. Yeah. No, so that's a remark I want to make later on. So basically, if we have, once we fix orientation on our graph, which is the orientation on, so each edge has orientation. So basically, choosing an orientation corresponds to specifying which one is plus and which one is minus. Exactly, that was the condition on orientation. Yeah. Okay, and then, okay, let me say, so the hyperplanes are a good way to also get the combinatorial distance back. So if we have two vertices in our cube complex, then we say that a hyperplane separates them, well, if he separates V1 and V2 if they are contained in different half spaces. Okay, and then I have two more facts about hyperplanes. So the first one is that the distance between two vertices is exactly the number of hyperplanes separating the two vertices from each other, the combinatorial distance. And then similar with this, you can then show that you have a path, so a combinatorial path. For us, yeah, from now on we'll only work with combinatorial path. Gamma from V1 to V2 is geodesic if and only if gamma intersects every hyperplane at most once. That's like very nice. So these hyperplanes really give us the way to measure distances, right? Like if you have a path and it doesn't cross the hyperplane twice, we know it has to be a geodesic. On the other hand, if there's a hyperplane that it goes in and out again, then it cannot be geodesic. Yeah, and then I write the remark of Mark that so an orientation corresponds to a choice of positive half spaces. So if we associate to each hyperplane a positive half space, like this one is positive, the other one is negative, that's the same as giving an orientation on your graph, because the orientation is just an orientation on the edges. Okay. Good. So these are the, this is kind of like hyperplanes. Good way to measure distances. You also have, like, just as a side remark, sometimes in group theory, people look at these spaces with walls. So essentially, it's kind of spaces where you have so-called walls that divide your space into two spaces satisfying certain axioms. So that's very closely related to that. So if you have a space with walls, you always can construct cat-zero cube complexes. Cube complex that gives you this space with walls, and this defines as a space with walls. Okay, but we will not go down that route. Now what I would like to look at next are isometries. So now we have some kind of understanding of distances in cat-zero cube complexes. And the next one is, like, we want to understand what kind of isometries can we have. Cat-zero cube complex. So, okay, there's one thing. We say that an isometry f of a cat-zero cube complex has an inversion along a hyperplane E. Well, if it preserves the hyperplane, and if it exchanges the two half spaces. Okay, that's an inversion, and it's not that these are all that bad for us, but it makes things easier if we consider only isometries that are not these inversions. And in our case of the Cremona group, or of groups of birational transformations, we have seen they preserve an orientation. So inversions essentially never appear, never happen. Yes, sorry. Yeah, thank you, of course. No, it doesn't need to fix the hyperplane. No, it really can also, on the hyperplane, it can be. No, it's not a Fourier 2, yeah. Okay, and then there's a theorem that was proven by. That's also it's proven by Haglund. It's also a fact about the cat-zero cube complex is if you have an isometry f of a cat-zero cube complex L. Then, and we assume that actually f and also all the iterates of f and act without inversion for all n. Then we just have two possibilities. So the one possibility is that f is elliptic. Which means it has a fixed point. Or the second option is that f is loxodromic. So I will explain it. No, in this case, it just means a fixed point in the cube complex. So in terms of vertex, just means it preserves the cube. But we'll see after if it preserves an orientation, then this will imply that it has a fixed vertex. Yeah, or the second option is that f is loxodromic, and in this case means that f preserves a well, again, combinatorial. But if I don't mention it, I always mean combinatorial. Geodesic, so bi-infinite geodesic. Geodesic line, and the restriction to this geodesic is like a non-trivial translation. Yeah, so basically there exists a geodesic line, and if that is preserved by f and can restrict it, and there's just given by translation. Of course, in general, there exist many such geodesics. It's not a unique one. But yeah, such geodesic lines are called anaxes. Of f. No, there exist many. I mean, you can always take like Z2, right? The square complex. It's clearly cat 0, and they just take a translation. Like then you have like completely. And that's the typical thing too. It's not like in hyperbolic spaces where you have unique geodesics. I don't think they need to be parallel. I don't think they don't intersect. Yeah. They don't. If parallel and that's not intersecting, yes. Okay. So maybe let's give some exercise. Maybe good to give exercises in a mini course. So if you look at the, it's not a hard exercise. If you define the length of f to be the minimum of all the distances between vertex x and its image, so combinatorial distance, right? Then we have that this length is 0 if and only if f is elliptic. Okay, this is straightforward, probably direct. And if has to think about is if F is loxodromic, then the restriction of F to any axis translates by this length. And then we can also see that, or we can also show as part of exercise that the length of F, this is exactly the limit of n goes to infinity of the distance between any vertex x and f of x divided by f iterated n times of f divided by n. Yeah. There's no parabolic case, yes, exactly. So that's kind of like the nice thing, yeah. Let me just make some, yeah. So, okay, this L of f is called the translation length of f. So, yeah. Yes, I see. Yes, that's true. We are mixing up here different distances. Okay, let's maybe take here the Euclidean distance, and here the yeah, okay, here is still here the combinatorial distance, maybe. It's true, thank you. Okay, let's just work with orientation preserving, and then it's good. That's good. But thanks, very good remark. Yes. So the important part here, but it's okay. The important part here is these things, just to see if it cannot happen that it acts by translations on, like with various translation lengths, right? Like if you have one axis, then the restriction to it is really given by a certain translation length. The other axis, it's the same translation length. You cannot have along one axis very fast and the other one very slow. This doesn't work. And yeah, so you have this unique translation length of f. Yeah, so here, okay. Let's not do this as an exercise. So this, yeah, with the Euclidean thing, it works. Yeah, it's not good. Let's just cross out this exercise. Because it's smaller than 1 if it is. But yeah, like the question before, like about the parabolic isometries. So the important part here is that that we really work with the combinatorial metric, because if we would work with the Euclidean metric, we would have parabolic isometries. So if you have like a cube of infinite dimension, and then you take a combinatorial axis within that cube, that's infinite, right? You just go further and further back in the cube. Then this gives you an isometry that is not loxodromic with respect to the Euclidean metric. Because within the cube, right, you walk here, then you have length square root 2, you walk one further, you have length of, like it doesn't grow linearly within the cube, that is, if you walk back. But with the combinatorial metric, this works well. And then the other remark is if we take away this assumption about that f to the n acts without inversion for all n in Z, then you have another type of isometries, which are these helixodromic isometries. So where your your isometry does not, it doesn't stabilize an axis, but it stabilizes, it has a geodesic line times a cube. And so it's kind of like a thick axis on which it preserves helixodromic elements. Yeah, but since we only are interested in actions that preserve cubes, we don't have to bother with these other types of isometries. Okay, then one last result I would like to tell you. That's a theorem by Gerasimov. I know it from a paper of Cornulier. So if we have a group that acts with by isometries on a cat-zero cube complex, say FL. So by isometries, of course. And we assume that it acts with a bounded orbit. Then G has a fixed point. Okay, so it shows a bit kind of like why cat-zero cube complex is it's stronger than just being cat-zero. So you have the result that if you have a group that acts on a complete cat-zero space with a bounded orbit, then it has a fixed point. But here, cube complexes, they don't need to be complete, right? I mean, they're infinite dimensional and very large, right? Kind of. So, but nevertheless, it is true that if you have a bounded orbit, then you have a fixed point. Okay, and then yeah, let's make this last observation, which I promised. So if you have a group that acts on cube complex, cat-zero cube complex L that preserves an orientation, and then G fixes a point if and only if G fixes a vertex. So if it's true for groups, it's also true for single elements. Like you just look at the element generated by this element. And I mean, for the proof, well, okay, one direction is clear, right? If it fixes a vertex, it also fixes a point. Vertices are points, so that's good. And for the other direction, we just assume that P is our fixed point. So if G times some point P in the cube complex is equal to P, now what we do is we take the smallest cube that contains P. So that's a finite dimensional cube. So okay, and this smallest cube then has also to be preserved by G. And now we can just look within this cube. I mean, now we have all these positive and negative half spaces. So we just take within this cube like the intersection of all the negative half spaces and the intersection of all the positive half spaces. So these are two vertices, right? The idea is if you have, let's say, cube here, and then we have one half space here, another one here, another one here, and now each of them has a positive and negative side. Then we just look at the place, at the vertex that's contained in all the negative ones, and at the vertex that's contained in all the positive ones. So these are two vertices, and they also need to be preserved by our group G. So if you have V1 to just be the intersection of all the negative half spaces in C, and V2 to be the intersection of all the positive half spaces in C, and then these are fixed by G. So we have a fixed vertex. Okay, so and the thing is, we are we are in the situation, right, where with our groups of birational transformations, where an orientation is preserved. So, like if we have a fixed point, we automatically have a fixed. Okay, so let's now go back to the our situation. So we go back to the action of BRS on the blow-up complex. Now, the question is, what are the hyperplanes in our blow-up complex? So how can we describe the hyperplanes? Well, let's have a look at how we describe vertices, right? So we start with a regular projective surface T with a marking, and now we blow up a point on T. So this defines us then H, and hence a hyperplane. So an H is given by a closed point P on a marked regular projective surface W phi. So basically, if we have such a triple, regular projective surface W, marking phi, and a point P, then this defines as a hyperplane. Because we have an edge and hence a hyperplane. And the question is now, if we have two such triples, when do they define the same hyperplane? So another question, when are the corresponding edges parallel? Okay, so we have the following lemma, I will briefly sketch the proof after. So if we have two such triples, W, phi, and P, and here we have W prime, phi prime, and P prime, they define the same hyperplane. And the claim is now that this is the case if and only if. So if you look at the composition of these markings, phi prime inverse composed with phi, so that's a map, birational map from W to W prime. So I say that this is the same hyperplane if and only if this is a local isomorphism at P, and we have that phi prime inverse composed with phi of P is equal to P prime. Yeah, so let me just give the idea of, sketch the idea of the proof with orally, so that we don't have to write too many pages. So one direction is, well, let's assume that this is actually a local isomorphism around P, and P is mapped to P prime. And we want to see that then this implies that they define the same hyperplane. So, okay, what we do is we have here our surface W, and here we have our surface W prime. And then here we have our map phi prime inverse composed with phi. And now what we do is we look at the Tarski decomposition here of this birational map. And okay, now we see essentially what we see is that, okay, here is a local isomorphism around P, and it maps P to P prime. So if it's a local isomorphism around P, then, well, we never blow up P here, and it's also not contained on any curve that's contracted here. So this means if we have here, okay, we have here our blow up that's given by blowing up P, and then here we blow up who knows what. But since P is not contained on, so it's not P that we blow up, here we have kind of like, we can still blow up P up here, so it's a parallel edge. And then we continue like that, and on the other hand, then we, well, contract our things on the other side, and P always, like the vertex given by blowing up P always stays parallel until we end up here on P prime. Yes, so the idea is basically if you blow up something here that's not P, then you can still blow up P up here. And this one is then parallel to the P down here. The same if you blow up another thing here, you can still blow up P. You can still blow up P here, and it's parallel again. And then the same with contracting. So after you contract things that are disjoint from your point P, so you end up. So it's a edge that's parallel and parallel and parallel. And in the end here, since we know that P is mapped to P prime, this corresponds then to blowing up P prime on this side. So it's the same. And for the other direction, let me also just give the rough idea. So if we know that they define the same hyperplane, this means in particular that W phi and W prime phi prime are both on the same side of, in the same half space, right? So we have here our W phi, and here we have our W prime phi prime. Now we know they are on the same side of, like in the same half plane, is defined by this by blowing up P, or here blowing up P prime. This means there exists here so this means there exists a geodesic line between these two vertices that never crosses this hyperplane. And now you can do a similar argument again. So basically, you just blow up, you contract, but you never. So it's like you never involve the hyperplane given by P, and then one can show that actually this implies that that it has to be a local isomorphism around P, and it's mapped here to P prime. So just roughly the Petrov idea. And yes, so and what we can get from this is the following lemma. So that's the following lemma, which says that the distance between two vertices in our cube complex, so between T phi and T prime phi prime, this is just the number of base points of phi prime inverse composed with phi plus the number of base points of phi inverse composed with phi prime. So basically just the inverse of this map. And again, the proof kind of similar. So if we have here T go to T prime, here we have phi prime inverse composed with phi. And now again, we take the minimal resolution, pi z here, and here we go down rho. Well, then again, this gives us a path of length of the good length. I mean, the number of points we blow up here is exactly the number of base points of this birational map, and the numbers of points that are blown up here is the number of base points of this birational map. So we get a path of length, well, number of base points of phi prime inverse composed with phi plus number of base points of phi inverse composed with phi prime. And this one is now a geodesic because here, because it's a minimal resolution, like there's no point that we blow up here that we also contract back to it. So with the previous lemma, we see like it crosses every hyperplane at most once. So we really get that this is a geodesic. Okay, so basically this is actually good. So this tells us that we can we understand what are the distances in our cube complex. So basically distances really correspond to the number of base points. Okay. Okay, and now we have seen that this action here preserves the orientation. So now we can apply Haglund's theorem, where we get that, well, so if we have a birational transformation of S, then this one is either elliptic, and as we've observed in the beginning, that's equivalent to saying that F is conjugate to an automorphism of a regular projective surface. Or it is loxodromic. And well, it's equivalent to saying that F is not conjugate to such an automorphism. And also, this means that it preserves an axis. Translation along an axis. But well, non-trivial. Okay, and so if it's not conjugate to an automorphism, then we know there exists an axis. So let's have a look at such an axis. So let's take a V, example, to be vertex V that's on an axis. That's on the axis. Of F. Okay, so this means that if we have here, well, okay, maybe not use the notation V. So if you have T phi here, and now, okay, here we have the axis, then at some point we apply Tf, then we have Tf phi, Tf square phi, etc. So now, since it's on the axis, we know that for all n bigger than 0, we have that the distance between T and F phi, between T phi and T F iterated n times and phi is the same as n times the distance between T phi and T F of phi. Right, that's exactly the meaning of being a translation. So each time you translate it, you just move by the same distance. So now we can translate this into our language of base points. So this we know that the so this distance here. So this is the number of base points of or the number of base points of phi inverse f to the n phi plus number of base points of phi inverse, and then we take the inverse, so f minus n phi is the same as here, the same as the number of base points, same as n times the number of base points of phi inverse f plus the number of base points of phi inverse f inverse of phi. Okay, right, we just apply our lemma directly. And now what we also know is that the number of so this number of base points of f iterated n times, or of this transformation, which n times is at most n times number of base points of this, right? Like if you compose two maps f and g, then the number of base points of f composed with g has to be smaller or equal to the number of base points of f plus the number of base points of g. Like yeah, we just blow up those base points. There could be simplifications, but cannot have more base points. Usual. So we know that this one is smaller or equal to n times the number of base points of phi inverse f n phi, and this one here so also smaller or equal to n times the number of base points of phi inverse f to the minus n phi. So this gives us that actually we have to have here and here equality. So we obtain that the number of base points of phi inverse f phi iterated n times is exactly n times number of base points of phi inverse f phi, and the number of base points of well, the same for the negative. Phi inverse f to the minus n phi is n times the number of base points phi inverse phi. Yep. Yes, no n here. Fine. Thank you. So basically, if we choose one that's on the so if we conjugate to our transformation f to a birational map of the that's on the birational with a birational map to a surface that's on the axis, then basically we have this stability, kind of like the base points, they never cancel each other out. Here we have a nice link to the courses of Charles and Serge. I'm not sure. They will probably speak about this in a different context. So the terminology, which I will just now use it as definition, is that means that phi inverse f phi is algebraically stable. So yeah, this basically this gives a nice geometric interpretation to the fact that if you have a birational map of a surface, it's always conjugate to a birationally to an algebraically stable map. Yeah, you will most probably hear today or one of these days why this is important and how this can help compute the dynamical degree. So this was known before, but gives like a nice geometric interpretation. Okay, and then what we want to do here, okay, we have seen yesterday kind of like the degree of a map and then the definition of the dynamical degree. So, but here we don't really work with degrees so much, or like we don't see the degrees in our complex. But what we do see is the number of base points, we've seen. And so we can also define the dynamical number of base points. Okay, it's a way less important and less interesting dynamical invariant of a birational map than the dynamical degree. But nevertheless, it is one. So the dynamical number of base points is given by so this is the, call it mu f, and it is just the limit of n goes to infinity. And we take the number of base points of f iterated n times divided by n. And this number was introduced by Jeremy, whom you'll hear, and Julie Desserty. And what we actually obtain from this whole story here is the following theorem, which was proved by Jeremy Blanc and Julie Desserty, at least for the case of characteristic 0 and algebraically closed, is that, well, this dynamical number of base points is always an integer. And 2 is actually, there exists a regular projective surface T with a birational map S to T, such that actually phi inverse f phi has exactly mu f base points. So actually this dynamical number of base points is realized on some surface. And well, then of course, like special case is of the second one is that this dynamical number of base points is equal to 0 if and only if f is conjugate to an automorphism. Yeah, and I mean this follows directly out of this this discussion, right? Like we have just go to a point on the axis, and yeah, there we have that it has to be it's mu f plus mu of f inverse. That's the translation length, and this is then exactly given by the number of base points here, and we also see. If this has to be, if this is 0, then it has to be conjugate to an automorphism. So also we see like the number of base points, like right from this one. So it's the asymptotic growth of the number of base points. So if this one has to be an integer, in that case, like the asymptotic, asymptotically, the growth of the number of base points has to be linear. Or if it is 0, then actually this one is bounded. So it's either bounded or of linear growth. There's nothing in between, so it cannot grow like some weird function. It cannot grow like the logarithm or something. So, you know, growth is linear or has to be bounded. Okay. Then another consequence that's direct now from this cube complex is the following theorem. So we say that a subgroup G of BRS is conjugate to a subgroup of a group of automorphisms for T regular projective surface. If and only if there exists a constant k such that the number of base points of f is smaller or equal to k for all f in G. Okay, so the proof of this is, well, so that's like a generalization of this this last statement, but just two groups. To say that we observe that the J fixes a vertex if and only if, and here we need the theorem of Gerasimov for one direction. If and only if the orbits of G are bounded. And okay, obviously if one orbit is bounded, then all of them are bounded. And this we see is equivalent to saying that, well, the distance of, well, if you look here, I like S and identity, and S and F. So this is globally bounded for all F in G. But here, by our observation before, this we see is equivalent to saying that the number of base points of F is globally bounded. This proves the theorem. I think maybe yes, but elliptic is a bit overused term sometimes, and then it's a bit tricky. What is an elliptic? Yeah, I think I would call such a group elliptic, but it's a bit tricky always, like, to also call groups elliptic, because then there's first of all there's actions on various spaces, and then depending on which space you act, it's elliptic with respect to this action, but not elliptic with respect to the other action. And then some people also think a group could be elliptic as an abstract group. Yeah, as a group acting on this space, it is elliptic, I would say. But then some people also would call an elliptic group a group where every element is elliptic, but this does not imply that it has a fixed point, right? So yeah, calling a group So I think that's a subject Anne Lanchou will talk to you about a lot in the third week. Subject she's very much interested, or me too actually. It's kind of like when you have a group acting on a space, so for example, these cat-zero cube complexes, such that every element is elliptic. When is the whole group elliptic? And there are various results in this direction, but we are still lacking a general result. So for finitely generated groups, you would like to have it. And it's a general interesting question if you have a group acting on some space with non-positive curvature, let's say a finitely generated group, such that every element has a fixed point, thus the whole group has a fixed point. And for cat-zero cube complexes, that's not true in general. Okay, let me give just one corollary I would like to remark from this theorem, which is kind of like, I think, another baby version of Weyls regularization theorem that Michel will explain you in higher generality. But so, okay, let's say, for example, BRP2. Now we don't say what's the algebraic group, but we can say we look at a subgroup of bounded degree. And now you can show that if a group has a bounded degree, then actually like the number of base points is also bounded. Like if you have a fixed degree, you cannot have more than a certain number of base points. Okay, so if you have a subgroup of bounded degree, this means also the number of base points is globally bounded for elements in G. So this means it is conjugate to a subgroup of automorphisms. Yeah, you see it's weaker, right? Like because, okay, we haven't seen yet what the algebraic subgroup is, but it's always this only tells you, it doesn't tell you that the algebraic group is regularizable. It only tells you that the k points, the rational points of the algebraic groups are regularizable, which is strictly weaker in over arbitrary fields than saying that the group is regularizable. But okay, still it gives a nice thing, and it's kind of like nice that we have this purely combinatorial geometric group theory proof of such a otherwise a strong, like a more difficult thing. No, not only. I mean, you can have automorphism groups that can be of unbounded degrees. We see it as yesterday, if you blow up 10 points, the surface is on the surface, so you can get it. So, is what is your this is true here for all fields. But yeah, as I said, you will get a better version of this corollary on Friday. Okay, then in that context of yep. Yes, I believe so. I would have to think about a moment. Yeah, something to think about. Now, I would like to go another thing. So there's this notion of groups with a property FW. So we say that a group has property if every action on a cat-zero cube complex has a fixed point. Okay, that seems quite a strong property. It's also a strong property. Or maybe you've seen such properties before, like if you've read the book of Jean-Pierre Serre, there's the on trees and amalgamated products. You've seen the property Fa, so a group that where every action on a tree has a fixed point. You see this a stronger property because a tree is a cat-zero cube complex, so if it has property Fw, it in particular has to have the property Fa. But the thing is, there exist quite a few examples of groups with property Fw, so it's kind of like very rigid groups in some ways have this. So the basic example is basically like SLN Z if n is bigger or equal to 3. So these are groups that have this property. So these groups cannot act without a fixed point on a cat-zero cube complex. And also another context where you've seen it is maybe you might have seen Kashtan's property T. And property T is actually stronger than this one. So if it has property T, it also has property Fw. But there exist groups that have property Fw that do not have property T. Okay, and now also what we get, basically a theorem that we get for free is, well, if we have a subgroup of birational transformations of some surface, then this has, so if this has property Fw, then B is conjugate to a subgroup of automorphisms. This theorem was also not new, so it was for, so Julie Deserty showed it actually for groups with Kashtan's property T. And then Yves Cornelier and Serge Contat, they showed it for groups with property Fw for algebraically closed fields. But okay, here we get all fields. Yeah, and actually that's all I've prepared for today. Maybe let me just explain one more application, just orally. One thing one can also get from this action is basically, okay, let's say we work over a perfect field. So if you have a perfect field, then the number of base points of your transformation F over the perfect field is kind of like just times a constant times smaller than the number of base points over the algebraic closure. So if you have the algebraic closure, so the base points over your perfect field is just kind of like Galois orbits of points in your algebraic closure. So if you fix the field, then there's like a constant that bounds it. So this means if you have a transformation, birational transformation, and you know it is conjugate over the algebraic closure to an automorphism of some regular projective surface, you already know that it also is conjugate to an automorphism of a regular projective surface over the field over which it is defined. So that's kind of also a nice application of this cube complex. Yeah, that's it for today. So what we will do tomorrow, okay, so tomorrow, in case you got a bit fed up with all the base points and blowing ups and stuff and this complex, good, tomorrow we start fresh. We will do new cube complexes, not just one, but several, But several ones is basically we'll look at cube complexes with isometric action of here x for x arbitrary. Okay, so thanks a lot.
Do we have any questions for for Christian?
What are the kinds of problems that arise in that theory if t is not regular, and why is t being regular but not geometrically smooth not a problem?
Okay, I mean, if it's not so if it's not regular, we can have like problem right then when we blow up, like it gets more involved, right? Like then we can contract things that are not necessarily just lines, or if you blow up stuff, and then the whole things gets messy. I believe probably you could construct a similar cube complex with some more technical difficulties without assuming it to be irregular. But then the question is, why would we want to do something like that? Because we know that every surface has a regular model, right? So we don't have to make our life harder than necessary. Now, the problem with being regular but not geometrically irregular is kind of like, why this is not a problem is basically we just take our surface, but what we need is that we have this Zariski factorization, and this exists for all regular surfaces. And yeah, what we need is if we blow up a point, we still get something irregular, and basically that's all we need for the construction of this cube complex.
So it's very similar to the Basser tree theory, yes?
In some ways, yes.
And whether the Basser tree is a part of cut zero.
Yes.
Always. So it's really part. But in the Dole theory, you have very important part which concern the behavior at infinity. So there are ends and here.
Yes, so there exist various notions of boundaries of cat-zero cube complexes. So for example, the roller boundary, or they have been studied. It's just like, so I remember some years ago we tried a bit look at this, but I don't really know of, I think most of the applications where this has been used to show things like groups is for finite dimensional cube complexes. For infinite dimensional cube complexes, you can define these boundaries, but yeah, I'm more interested in the applications, and I haven't seen any applications kind of like what this would be. But one can define it, and I think for finite dimensional cube complexes, they are even used to show like certain forms of Tits alternative, like that.
For surfaces, there is this also theory of Danilov and Pisatoulian.
Yes.
What is the relation?
Yes, that's a good question. I mean,
They work with automorphism groups.
yes. In some ways, their arguments are much more refined in some ways, right? Like they really look at the various blow-ups configurations that you can have, and here in some ways we don't care too much about how the exact intersections and things look like. It's just the question is, can be contracted or not, and that's it. But yeah, could be that there is some way one could refine this or see this more geometrically, but I don't know of any. But I think it's a
I'm confused about the, you say the corollary, the subgroup is of bounded degree. I think the degree is defined by the intersections of line bundles.
Yes.
And you say there is the base point, the number of base point is bounded. So how to deduce it?
So basically the fact that we use this, that if you have a transformation of bounded degree, then also the number of base points is bounded by some constant depending on the degree. So you can, if you just look at proper base points, it's kind of clear, right? You look at the common zeros of all your polynomials. So if they're of bounded degree, they cannot, like the number is bounded by 3 or of something. Okay, and then you can do similar arguments by also for infinitely near base points. Go up something. Number of base points, then you do similar arguments. Go with this. Roughly.
This is a mic, right?
Yeah.
Okay. So I think that these all things are very similar to this birational, the group BRS acting on this infinite dimensional hyperbolic space. In the sense that when you act on the infinite dimensional hyperbolic space, then the intersection form the inner product on the hyperbolic space. It is the catching the dynamical degree.
Yes.
And
yes.
in this case, in this cube complex, we are detecting the dynamical degree of the base points. So
exactly.
I
Yes.
see that these two are so similar theory, and these elliptic and parabolic. Well, parabolic doesn't occur here though, but so is there a direct comparison of this infinite dimensional hyperboloid and this ket zero cube complex? Is there a quasi-isometry? Probably not quasi-isometry, but I think there might be some morphism between these two.
Oh no, not that I know. The thing is, in some ways, that's the way I said. The hyperboloid is better than the cube complexes because it's finer in the sense that there are more loxodromic elements. You take automorphisms, surfaces of unbounded degree, right? So then they have positive dynamical degree. This means they act by loxodromic isometries on your hyperboloid. Whereas here on this cube complex, they have a fixed point. So in some ways, one of them is rougher and the other one is finer, more nuanced. So it's exactly it's the infinite dimensional hyperboloid kind of captures the length function given by the degree or the logarithm of the degree, and this one captures the length function given by the number of base points. But the degree is kind of the nicer variant, just because you can have many very rich. So I don't. Yeah, no, they kind of cat zero means basically non-positive curvature, so it has big flat parts, right? It has these giant cubes that are completely flat. The hyperboloid is really kind of everywhere negatively curved. So you would have to bend this base somehow. Very abstractly you could define it. Then you would lose lots of. I don't know exactly.